Hey, welcome. Today we are talking about one of the coolest tricks in the entire AI playbook, data augmentation. This is the secret sauce, the magic ingredient that takes an AI from the sterile lab and gets it ready for our messy, unpredictable world. Let's get into it. So here's the fundamental problem that every AI faces. You can spend a fortune training your model on thousands of hours of perfect, clean data. Like a self-driving car that's only ever seen a perfect, sunny California day. But what happens the moment it hits the real world? An unexpected foggy night? It can fail, and fail catastrophically. That perfect training data actually makes the AI incredibly brittle. So how do developers get around this? Well, that's what we're going to unpack today. We're going to start with exactly why that perfect AI fails. Then we'll dive into the art of augmentation itself. We'll see how you can master light and color with just a single line of code, literally bend space and perspective, and even simulate a chaotic, rainy world, all in the name of engineering a much, much safer AI. All right, so let's dig into that first big hurdle. It really all boils down to two key ideas that you hear all the time in the industry: the domain gap and the long tail. You see, this domain gap is basically the chasm between the training room and reality. A model that was meticulously trained on those sunny California roads, well, it's in a completely different universe, a different domain, when you drop it into a London downpour. The rules of light, of color, of visibility, they've all changed completely, and the model just gets lost. And that brings us to the second killer problem, the long tail. Just think about all the possible things a self-driving car could ever see. 99% of its life is just boring, clear weather driving. But those critical events, a deer jumping out at dusk, a sudden blizzard, a tire in the middle of the highway, they're incredibly rare. You could drive for millions and millions of miles and just never happen to collect that specific, crucial piece of data. It's just not physically or financially possible to capture every single one of these edge cases. So if you can't find all that weird, rare, out-of-domain data, what do? Well, you make it. This is where the art and science of data augmentation comes in to save the day. It's all about getting your AI ready for game day. At its core, data augmentation is the technique of taking the data you already have and just creating new, tweaked, modified versions of it. But here's the key. We're not just creating more data. We're creating smarter data. We're creating data that specifically teaches the model how to generalize, how to be flexible, and how to handle the stuff it's never seen before. The best way to think about it is like an athlete's training regimen, right? A champion football team doesn't just practice on a perfect, sunny field. No way. They train in the pouring rain, they train with fake crowd noise blasting, they practice drills from every weird angle imaginable. They simulate adversity so that when the championship game comes, nothing can surprise them. That's exactly what we're doing with our AI models. Okay, so let's get our hands dirty. Where do we start? Well, we start at the first and most fundamental level of engineering reality, mastering light and color. And believe it or not, it can all start with a surprisingly simple piece of code. Now, don't worry about the syntax here. That's not the point. The point is to see the control that developers have. With this one little line, they're basically telling the computer, hey, take this image and on the fly, I want you to make it somewhere between 10 and 20% darker and also just slightly dial down the contrast. They are literally engineering a new reality one parameter at a time. And this technique, this magic trick, has a name: photometric augmentation. It's all about changing the values of the pixels themselves, the light, the color, the brightness, without messing with the actual structure or geometry of the image. This is the toolkit for making an AI robust to different times of day, from the harsh glare of noon to the soft glow of dusk. And boom, here's what that actually looks like. On the left, you've got the original photo, taken during the day. And on the right, after applying that simple line of code, we have a totally believable simulated evening photo. We've just instantly doubled our useful data. We can now teach our model with this exact same scene, looks like at noon and at 7 p.m., and we never had to send a car or a photographer out there again. Okay, so we've got a handle on light. That's a huge step. But the world isn't just about light and color, right? It's three-dimensional. So let's level up and talk about bending space itself. This is where geometric transformations come into play. Now, instead of just changing the color of the pixels, we're actually changing their position. We're rotating the image, we're scaling it, we're cropping it, we're warping the perspective, all to simulate seeing an object from a slightly different angle, a different distance, or from a different camera position. But this is where things get really interesting because, as you can see, it's a strategic trade-off. For example, random rotation is fantastic for something like aerial surveillance, where a plane can see a building from literally any angle. But check out that risk column. It can be a total disaster in other areas. Or take random cropping.
It's a great way to teach an AI to recognize a product on a messy retail shelf, even if it's partially blocked. But what if you accidentally crop out the object you're trying to teach it to see? It's a really powerful but very delicate balancing act.
And this quote just hits the nail on the head. This whole process is not some blind automated thing you just switch on. It requires deep, deep knowledge of the specific problem you're trying to solve. If you're building a system to read, say, numbers on a check, and you just blindly tell it to rotate images, you will actively teach your model that a 6 is sometimes a 9. You're not helping, you're literally poisoning your own data. So we've manipulated light, we've bent geometry. But what about the really hard stuff? What about simulating the very air that the light is traveling through? Well, welcome to the true frontier of augmentation, simulating the chaotic, physics-based effects of the world around us. I mean, simulating something like rain or fog is incredibly difficult. You can't just slap a gray filter on a picture and call it fog. That's not how it works. Real fog gets denser the further away you look. Real rain creates reflections, it makes surfaces wet, it splashes. To do this right, you have to simulate the actual physics of the atmosphere and how light behaves as it moves through 3D space. Look at rain, for instance. A really high-fidelity simulation breaks it down into 3 distinct physical problems. First, you have to simulate the streaks of rain as they fall through the air. Okay, makes sense. Then, and this is the really clever part, you have to change the physical properties of the road surface to make it look wet and create realistic reflections. And finally, you simulate the droplets hitting and distorting the camera lens itself. It's a multi-layered simulation. And it's the exact same idea for fog. The best simulations use a physics model, something called the atmospheric scattering model. They take a 3D depth map of the entire scene and then apply fog in a way that truly respects distance. It's thicker and more opaque way in the back than it is up close. And this isn't just for cool special effects. This is absolutely vital for validating the safety of an autonomous vehicle. It lets you certify that the car can operate safely down to a specific visibility, like say 150 meters. So, after all that, manipulating light, bending space, simulating physics, let's bring it all home and talk about why engineering data this way has such a massive strategic impact. The numbers really do speak for themselves. Studies have shown performance improvements of up to 28% when models are trained with these kinds of techniques. Now, for a self-driving car, a 28% better ability to understand a foggy road, that isn't some minor tweak. That is a game-changing leap forward in safety and reliability. And what this all points to is a huge strategic shift in the entire field of AI. For years and years, the focus was model-centric. Everybody was chasing a slightly better algorithm, a slightly fancier neural network. But now, the industry is making a massive pivot to a data-centric approach. The new competitive advantage isn't just about the model you use, it's about the quality, the diversity, and the cleverness of the engineered data you feed into it. Building better data is the new frontier. Which leaves us with a final thought to chew on. We've all heard that phrase a million times. Data is the new oil. But oil is a finite resource, right? You have to find it, you have to drill for it, and eventually it runs out. So if that's true, is this engineered data, data that we can create and scale almost infinitely, the new renewable energy for AI? Something to think about. Thanks so much for joining us.